Welcome back to the lecture 10. So in this lecture I will discuss about the modeling of the adsorption process so that you can understand how to model the CO2 capture. I will show what are the necessary equations. Okay, it could be the mass, momentum and energy balance equations that are required to design and optimize the packed bed adsorber. So there are if you see, there are two types of terms and we used to classify them: pre-combustion capture and the post-combustion capture. In pre-combustion capture we partially oxidize the fuel, the fossil fuel that we would like to burn, and it creates the CO2 and H2. The produced CO2 and H2 will be separated, okay, and the hydrogen will be used for the energy generation. That is the pre-combustion capture. Okay, then that means before combusting the hydrogen to produce the energy, we are separating the CO2. That is a pre-combustion capture. In case of the post-combustion capture, we will burn the fossil fuel and it produces the flue gas. Along with that, CO2 will also come. So we will install our capture setup to separate the CO2 from the rest of the gases. Okay, that is a post combustion capture. So in both the cases, the location of this adsorber, the packed bed adsorber, will change whether it is before and after the combustion process. Okay. So the source to this adsorbent bed is very important, and what is the concentration of the CO2, that plays a major role in getting how much pure CO2 from the output. So that is one of the important parameter that we need to incorporate in our model, and also we will see what are the other parameters we need to consider. So here we can see the left side graphic that is showing the adsorber. If our feed contains two gases A and B, okay, and we would like to separate A and B, okay, we have a adsorbent, that is a solid that is packed inside the bed here, and from the other end we can see that raffinate coming, that is a pure B. That means the bed is adsorbed the gas molecule of A due to the affinity between the A and the adsorbent. The most of the A is adsorbed on the bed. So here we can see the mass transfer zone and also how the concentration of the gas molecule A is changing with respect to time. So as the process is proceeding, it is proceeding forward, then the concentration of A at the exit is increasing. Okay, once the bed is saturated, then we observe the concentration of A at the exit. Okay, that is what the breakthrough we discussed in our previous lectures. When it comes to the desorption, desorption can be done multiple ways. As Dr. Debanshu discussed, we can go for thermal, external thermal source, and we can also inject the heat from outside, and or else we can use some purge like any inert gas that will disturb the interaction between adsorbent and also the adsorbate. Okay, due to the reduction in the interaction, the gas molecules that are adsorbed in the bed will come out. Okay, that is the physics behind this purging. And also we can reduce the pressure in the bed. That is how the pressure swing adsorption works. If the gas is stored at high pressure, for example 10 bar, if we are releasing the pressure valve at the exit to the atmosphere pressure is 1 bar, okay, whatever the gas that is stored, that will come out, that is a pressure swing. And if we are supplying heat, okay, that means we are increasing the temperature, the desorption takes place by increasing the temperature, then also we can dissolve the gas that is adsorbed in the previous step. So if we continuously doing this, okay, first adsorption, and whatever the gas that is adsorbed, the desired gas that is adsorbed, we will use either purging or any of the regeneration method we will use to get the A back, and again we will feed the flue gas, okay, and to get the pure gas and also desired gas out of it. If we keep on repeating this, this is a adsorption cycle. This process is called the cycle. There are multiple ways of doing this. We have pressure swing adsorption, temperature swing adsorption, okay, and there are hybrid swing adsorptions also. In the coming lectures, we will discuss those techniques. So now we will see on this the fundamentals which you learnt from Dr. Ravi's lectures and also Dr. Debanshu's lectures, where we discussed what is the adsorption and what is the diffusion, how what type of resistances we observe in the packed beds, how those resistances would affect the final output, and also if we are considering all those various physics, okay, how many different types of mathematical models that will form, okay, various partial differential equations we will see. All those equations we will discuss in this lecture. So design of a adsorption process that requires development of a model, okay, which describes the column dynamics. So the term model representing here is a mathematical equation. In our engineering processes, we write partial differential equations that defines the physics of that process. Okay, then we call that as a model, the mathematical model that could predict the experimental behavior. Okay. So what is the dynamics of adsorption? That means how the concentration of the gas, adsorbed gas, that would change, and if it is a exothermic process, the temperature change takes place in the bed, how the temperature that is changing with respect to time, and also the pressure, okay, how the pressure will change from inlet to the exit, and also how it is changing with respect to time, okay. All those various conditions, how it will change during the process is called the dynamics of the adsorption. So the absence of the accurate and efficient model, generally we will if we have very accurate model, mathematical model, okay, we don't need to conduct multiple number of experiments, okay. One single experiment would be enough to develop a model. If we would like to design or optimize that process, we will use that model, okay, to get or generate the data. So I hope you will recognize this. So adsorption isotherms we estimate by changing the pressure. We will calculate the adsorption amounts, okay, at different temperatures, for example T1 and the T2. Okay, if I am conducting one experiment, that experiment is giving me the value of okay, if I pick one point here at temperature 1 and the pressure 1, that is the value of experimental data point. Okay, if I have a model at that same temperature and the pressure, if my model is predicting the same value that I am getting from the experiment, okay, the accurate model, that means the difference between the data points of both the model and also the experiment is almost close to the 0, okay. Then we don't need to go for this robust time consuming experiments. We can use these models to generate the data and to optimize the system. So that is the basic idea of learning the model. So the empirical design of adsorption column through experiments is very time consuming and expensive. So initially we can do some basic calculations for design. If we assume some length of the column and also the diameter of the column, and we will pick what is the size of the adsorbent that we are packing, and based on those calculations we will find what is the purity of CO2 that is coming out. Okay. If we are happy with that purity, okay, we will end that process there. But if that is not meeting the demand that we are expecting, okay, then we will modify the dimensions and we will either change the adsorbent and we will run that experiment again, okay, and till we reach our demand, we will keep on continue this. This is how the experiments work for multiple iterations. Okay. If we are having one very good model, okay, that model could predict the experimental result well, okay, in one day or 1 week we can get these results without conducting the experiments. So, what do we need to have a very good model? We need to understand the adsorption equilibria and also the kinetic parameters. You have seen the breakthrough curves, right? If we would like to model the breakthrough curve, we need very good model, kinetic model that could predict the breakthrough curve, and also we need equilibrium model that could also predict the experimental data exactly. So, these are very important parameters that we need to understand first when we are trying to design a adsorber. So, this fixed bed column, the mathematical simulations that would incorporate transport phenomena, how the mass is changing from entry to the exit and how the pressure is changing, and this is an exothermic process. So, we are interested in temperature changes also. So, we need energy balance equation. So, all the transport phenomena is important for both adsorption and the desorption cycle. At the time of adsorption and also during the time of desorption, that is one cycle. Okay. If you would like to optimize, if you have some specific quantity of CO2 that is coming out of the bed, or what is the productivity or the purity of the CO2, okay, you can optimize various parameters or operating conditions, okay, by using this model. Okay, is that enough or should we validate our model? What is the importance of validation? Why should we validate the model? Correct. Yeah, so based on the physics, we are developing the model. Okay, once we have a result, we need to validate that with experiment, at least one experiment, okay, to get confidence that this model can be utilized for other generating the other data points, okay, for various conditions. So, that is the idea. So, we will verify our model with the experimental data that is available, okay. We can pick the information from the literature and we will compare our model results with the experimental results. It could be the breakthrough curve or adsorption isotherms or the performance metrics. So, to predict the column dynamics, various set of coupled partial differential equations we need. We will see all those equations, various PDEs with mass, momentum and energy balance equations which must be solved. So, I will go through the overview. So, in this particular study, when we have a source that is a flue gas, okay, when it is in contact with the packed bed, we have gas solid phase, okay. We have two phases where CO2 will come in contact with the solid adsorbent. So, the dynamics of the column requires the gas solid equilibrium, how much amount of the adsorbate that could transfer onto the adsorbent, and what is the capacity of the adsorbate that is accumulating on the adsorbent. That is that information we will get it from the gas solid equilibria. So, and also the complexity of these models. So, when we are taking these porous materials, porous adsorbent materials, the diffusion and the film transfer is very important. That will make our model, the mass transfer, very complex. Okay. So, if it is more complex, then there are multiple calculations are required to get the accurate result. So, what gas solid equilibrium decides? It decides the limiting capacity. Okay. If you remember the type 1 isotherm, right, it would saturate at one point. Okay, that capacity limit we will understand from the gas solid equilibrium. Our adsorption isotherm will tell what is the limiting point, what is the capacity. And mass transfer zone is also decided by the gas solid equilibrium. So, if you remember the breakthrough curves, okay, after some point CO2 was observed at the other end. Okay, slowly it will start. Right. So, this mass transfer zone is also actually depends on the gas solid equilibrium. What is the adsorption, how much amount of the affinity that is present in between the adsorbate and to the adsorbent particles. So, now the first parameter we will note down, that is the adsorption equilibrium. Okay. So, this is one of the parameter that we need to model the packed bed accurately. So, we will go one by one, what are the various characteristics that we need to build a accurate model. So, first information that we need is adsorption equilibrium. So, another important point, so adsorption is an exothermic process. When we have these high concentrated flue gases, the flue gas that contains very high CO2 amount, okay, that will release the more heat. So, when it is releasing more heat, the heat should distribute equally. Okay. Can we consider isothermal process in this case? Is it correct? The question, did you understand? When can we consider isothermal? Temperature is supposed to be constant. Okay. Unfortunately, we are going for the porous materials where the thermal conductivity is very poor. Okay. When the thermal conductivity is poor, so this is how our bed looks like. Okay, there are pellets which are packed. The pellets are the porous pellets. It could be the metal organic frameworks. Okay, the carbons, zeolites are coughs. So, when the gas molecules are coming in contact with the adsorbents, okay, it releases the heat. The heat supposed to distribute equally. If the thermal conductivity is very good, then the heat will distribute rapidly throughout the bed. Okay, then the isothermal assumption we can consider. However, due to the poor thermal conductivity, we may observe the hot spots in the bed, okay, where there is heat that is present, and this will disturb the incoming gas adsorption also. Okay, whatever the CO2 that is coming into the bed, it requires the low temperature. Low temperature prefers good adsorption. However, due to the hot spots, the gas would not adsorb this. So, to model this behavior, to understand how the temperature that would affect the adsorption amount, we need to have energy balance also. So, the temperature effects are very important along with the mass balance. I hope you convinced with that physics, right? Why we need energy balance equation. So, in addition to the mass transfer will tell us how much amount of the gas that is adsorbed and how much amount that is diffused in the bed. Okay, and energy balance is required to understand how much heat that is generated, okay, how much that is affect the incoming adsorption. So, along with that, we need to understand the axial pressure. Okay, if based on the particle size, the pressure drop will be changed in the bed. Okay, if the particle, if the axial pressure along the bed is increasing, we need to estimate that change in the pressure in the bed. Okay, and that information we will obtain from the momentum balance. Okay, that so far we have discussed how the species balance, that is the mass balance equation, that will tell us what is the concentration of the CO2 and other species in the bed, okay, along with how much amount that is adsorbed. Then we have energy balance equation that gives us the information of the temperature, how much temperature that is accumulated, that is generated, and then we need to understand what is the pressure, how the pressure is changing inside the bed. Okay, now coming to this various length scales that are involved in this system, this is a very nice figure where the particles, the pellets are packed, okay, which are porous pellets. This adsorber that we see is in 1 meter length scale. Okay, then we have a pellets where the gas is diffusing through the voids of the pellets inside the bed, and then in the pellet we have a pores. The pores, macropores, and also inside the particles also there are micropores. Okay. So at the particle level, okay, less than nanometer in the angstrom scale, we see how the CO2 interact with each other, and also how CO2 interact with the adsorbent. Okay, to design one or optimize adsorption process, okay, we need to understand the physics from the small scale, that is molecular level, the interactions between the adsorbent and the adsorbate, and also the mesoscale, how the gas that is diffusing through the macropores and also the mesopores. Okay, that information we will get it from the mesoscale, and also mass and energy balance in the pellets and also in the bed. Okay, this information is very important to get a accurate model. Okay. So if we carefully observe, the adsorption is happening here, okay, and gas particle will diffuse through these pores of the macro pore of this particle pellet. Then there is a micropores inside the particle, okay, and also gas is diffusing through the voids of the bed. Okay. So we will quickly see what are the things we learnt and what are the important parameters to consider for modeling this behavior. So first thing is adsorption equilibria. Okay, adsorption equilibria tells us how much amount of the gas that is adsorbed on the surface. Okay, we will consider this adsorption equilibria by using adsorption isotherm models. Okay, we will incorporate adsorption isotherm model that gives us the information how much amount of gas that is adsorbed. Then selectivity. Why selectivity is important to consider? Yeah. So there are two types of selectivity: adsorption selectivity and the diffusion selectivity. What is the difference? I have. Please. So when we are having the flue gas, okay, all of us interested from this particular topic, we are interested on CO2. Okay, rest of the gases right now we don't want those rest of the gases. We want CO2 to be stored in the bed. Okay, so when we are selecting the adsorbent, it has to be CO2 selective. Okay, if it is adsorption selective, the adsorbent must have a good interaction, okay, strong bonding with the CO2, that is adsorption selective. If it is a diffusion selective, comparing with other rest of the gases, CO2 diffusion difference is important. Okay, other gases should come out of the bed quickly compared to the CO2, that is a diffusion selectivity. Okay, if somebody is saying that their system is adsorption selective, that means bonding of CO2 with respect to adsorbent is strong. Okay, if it is a kinetic selective, okay, that means the diffusion of the other particles are faster, which are going out of the bed quickly compared to the CO2. Okay, those are the driving forces. That's why we have a breakthrough curve, and also we have adsorption equilibrium. Both are very important in modeling the behavior for CO2 capture system. Yeah, kinetics, we will get that information from the breakthrough curves. Okay, we have linear driving force models, and we have a couple of other models which will pass this information to the uh, mass balance equation. Then heat of adsorption, we will estimate the heat of adsorption as we discussed in our previous classes. This heat of adsorption, to which balance equation we will feed this information. We have mass balance, momentum balance, energy balance, right? Where this information will be useful? Energy balance. Okay. So whatever the amount of heat that is releasing, okay, that is a heat source. Heat source is a term we will use in the energy balance equation. Okay, that will tell us how much heat that is releasing and how it would affect the temperature in the bed. Then again, coming to the pressure drop, the pressure at the entry of the bed and also the exit of the bed are not same, okay, because there is a packing of the particles in the bed that would cause the difference in the pressure. Okay, we are interested in the pressure, and we would like to estimate the pressure change by momentum balance equation. Okay. So now coming to this analysis, so in fixed bed column, the mathematical models predict the transient behavior of concentration and temperature profiles. We will see equations one by one, okay, then you will get a clear picture of what I am talking about. They are complex partial differential algebraic equations, and which are mass, energy, momentum conservation. So also we will incorporate how the mass transfer rate, how the CO2 that is transferring from the gas phase, that is a bulk phase, to the surface, okay, and also equilibrium adsorption isotherm models will incorporate in the system, okay. That will tell us what is the capacity of these models, and also the thermal effects and the pressure effects. So first, starting with the fluid phase material balance, this is a equation for the fluid mass balance. Okay, this contains the accumulation term, okay, that is dou Ci by dou T, and there is an axial dispersion term. When this gas that is diffusing are entering from the bed, okay, we have a convection term, and also we have diffusion term. Okay, this is a dispersion term, and we have a convection term through the bed in the axial direction. Okay, and what is this term? No, not 1 minus epsilon by epsilon, the entire term. What is this term? So the accumulation of the gas pieces due to the adsorption. Okay. So if you observe, Q is the term, okay, that is the adsorption amount. The Q, we will get that information from the adsorption isotherm model. Okay, that adsorption isotherm, we will use the model to fit the experimental information, the Excel sheet which I have shared in our previous tutorial. Okay, that is your adsorption isotherm information. Okay, we will fit one adsorption isotherm model to the data, and we will use that model here. Okay, that is how we will get that information. So there is this term axial dispersion. We can, so most of the cases we have these assumptions. We will assume a few things to simplify these partial differential equations. Okay. So when we have a plug flow pattern, okay, there is a negligible axial dispersion. In that case, the convection will be, if we assume that convection is dominating, then we can ignore this second order PDE equation. So that is one way of simplifying it. Now coming to the kinetic models, the kinetic models are like a subsection in the species balance, these mass balance equations, because there is this term called dou Qi by dou T. Okay, how we are getting the Q? So that is a very important information we need. So the dou Qi by dou T, we can tell that as a overall rate of mass transfer for component I at time t, okay, which is averaged, the 2 bars that you see, right, that is averaged quantity. So, mass transfer kinetic models depends on assumption. We can assume that local equilibria, local mass equilibria, that means the amount of gas that is adsorbed, okay, which will be equal to the Qi bar. So, this local equilibria simplifies the mass balance equations. At rapid mass transfer, so when gas is entering the feed, okay, first it will touch this solid, the porous solid pellet, okay, the pellet is like that, which contains the pores. Before reaching the pellet, there is a film resistance, okay. So, and also there is gas that is adsorbed on the surface, okay, at the equilibria. So, what this local mass equilibria assumes that there isn't any film resistance and also the diffusional resistance. I am assuming that dou q bar by dou t is directly equal to the adsorption equilibria amount, but that is not exactly correct for the real case. We will see how the dou qi double bar by dou t is equal to, and also we will consider multiple diffusional and the film resistances in between. Okay, this Q star is there, right? Q star is nothing but the adsorption equilibria, the adsorption amount that we estimate from the experiments. Okay, so local equilibria is an assumption that we consider to simplify this kinetic models. Okay, where dou q I double bar by dou t is equals to dou q star by dou t. If you are considering this assumption, you are not worrying about macropore diffusion, micropore diffusion, and the resistances, film resistances that are coming into the picture inside the pellet. You are simply considering whatever the average of Q that is accumulating on the particle is equal to the amount that is adsorbed. So, that is the simplification from this assumption. Yeah, here you have very nice picture. Okay. So, when there is a gas particle that is coming here, okay, around this pellet we have a film resistance, that is the external fluid film resistance. If you recollect from Dr. Ravi's talk, okay, there is a film mass transfer coefficient also we will use. So, inside this pellet we have these macropore resistances, okay, how the gas molecule will diffuse through the pores, macropores, okay. Then so this pellet is formed by combination of multiple particles. Particle also contains the pore, okay, they are micropores. So, micropores also contains a resistance, okay, that is a micropore resistance. So, what we are trying to figure out here, in case if we are looking for a very accurate model, we need to consider micropore resistance and macropore resistance and also the film resistance. So, we will look one by one closely, okay. So, mass transfer from the fluid to the solid phase occurs is the very important step. That is where the film transfer resistance we consider in the packed bed. If local equilibrium theory is reliable, okay, only for the adsorption selective systems. Okay, when can you consider the previous assumption which I made? Okay, whenever there is a adsorption selective system, there is a strong adsorption is happening, but not for the kinetic selective system. If the diffusion is playing a major role, okay, if there is a difference between the diffusion of your CO2 to the rest of the gases in that adsorbent, then you better consider all those resistances, okay, the diffusional resistance in the macropores and also the micropores. So, what are these potential resistances? The external fluid film means around the particle there is a resistance, that is a film resistance, okay, that we learn in the mass transfer. And inside intraparticle diffusional resistances, in our case there are two intraparticle resistances, okay. One is macropore diffusional resistance, that means if there is a pellet, how the gas is diffusing through the voids of the pellet, that is a macropore resistance. Then we have a micropore diffusional resistance. Micropore means the particles having the voids, having the small pores, okay, how this gas molecules is diffusing through the pores of that particle, that is a micropore diffusional resistance, okay. So, coming to this external fluid film resistance, the concentration difference across the boundary layer surrounding the each particle will give us this film resistance. Okay. Here you can see how dou qi by dou t can be calculated as Ci, that is the concentration in the bulk phase, to the Cpi on the concentration of this gas on the adsorbent surface. Okay. So, there is this term diffusional resistance. If 3 by rho Rp epsilon P dPi by dou Cp I by dou R, this is a gradient. This is a concentration gradient from the surface of this particle to the center. Okay. This also tells us the information of dou q by dou qi by dou t. So, now we will start with macropore first, then I will show what is the micropore resistance. Okay. So, the diffusion molecules escaping from adsorbent force field during the diffusion of macro and the mesopore is called macropore diffusion. So, macropore means, do you know the size of the macropores? Anyone? Yeah, greater than 50 nanometer. If it lies in between 2 to 50 nanometer, we call it meso. Okay. If the diffusion is happening in that size range, we can put that in macropore diffusion. So, the gas molecules transport that depends on mean free path, okay, and the magnitude of the adsorbate molecule. So, when molecule mean free path, okay, is more than the pore diameter, okay, we call that as Knudsen diffusion. Okay, Knudsen diffusion dominates the transport. So, during that case, what happens? The collision between the gas molecule and the pore walls will take place. Okay. So, Knudsen diffusion does not depend on pressure, it depends on the temperature. We can estimate the dKi, the Knudsen diffusion coefficient, by this formula, where we can see the temperature that would affect the diffusion coefficient. So, this is the equation we will use to estimate the concentration of the gas, the CO2, okay, that is diffused through the macropore. Okay, this looks similar to the bed equation. However, here the accumulation inside the particle, okay, inside the pellet, and also the how much amount of the gas that is adsorbed on the micropore or the particle, okay, not on the pellet. Okay, this is again the diffusion inside the macropore. So, if the molecular mean free path is smaller, okay, then the pore diameter, the bulk molecular diffusion will be dominating. Okay, that is one of the information useful. We can use the Stephen-Maxwell equation or multi-component systems or Chapman equation that can be used to estimate these coefficients. So, the collisions between the molecules is also another resistance that we observe in this case. Okay, so if you would like to incorporate the macropore diffusion, okay, we can use this equation where these are the accumulation terms in the gas phase, in the adsorbed phase, okay, and the diffusion term. This is okay. This is this equation representing which location? Are you following me? So first we looked into the bed, okay. The first, the big equation I have shown, the accumulation, that is followed by convection, diffusion, and the adsorption. So that is for the bed. So this is for the pellet. Okay, inside the bed there is a pellet. Okay, we would like to find what is the concentration of the adsorbate inside the pellet also. So if we solve this equation, we will get the concentration inside the pellet. Still, this is not over because the particles that are forming the pellet also contains the pores. So that is called micropore diffusion. Okay. So the micro are the small pores which are in the range of particle size. Okay. The particle diameter is not much greater than particle diameter, which is close to the particle diameter, so that the molecules cannot escape easily. So in this case, the transport occurs by hopping, by jumping from one adsorption site to the another adsorption site. Okay. In general, intraparticle diffusion which is neglected in this type of micropore diffusion. So now what are the resistances inside the microparticle, which is one is micropore mouth, that is the opening of the micropore. Okay, inside this, okay, if for example there are particles like this, okay, this is a pore mouth. So this is another resistance that we observe in the micropores, and also distributed micropore interior resistance. Inside also there is another resistance. So if your system that is controlled by barrier resistance, then we will simply use this term K multiplied by difference between equilibrium value, equilibrium adsorption value, and the concentration that is outside this particle. Okay, that is similar to the film resistance that we have observed. And if it is dominated by interior resistance, okay, then we will consider this equation, the diffusion inside the particle. Okay, so d mu I is the micropore diffusivity. That is the equation we will use to incorporate the micropore diffusion. Okay, now you might have bored that we have multiple things to make our model very accurate. How to simplify that? Either you can go for local mass equilibria, okay, but your system is kinetic selective. Okay, then we have an option called LDF, linear driving force model. Okay, linear driving force model is very simple. That is, if we are taking dou qi by dou q star by dou t is the local mass equilibria. Instead of that, if we are considering that dou qi by dou t is equals to k multiplied by qi star, means that is the adsorption equilibrium amount. Okay, qi bar is the amount how the concentration of adsorbate that is at that point that is changing. Okay, so now interesting factor here is what is K. Okay, so how this main motivation behind developing this model is to simplify the diffusion resistance models and the film resistances that are inside these particles, intraparticle diffusional resistances. So what we did here is we combined all the three resistances into one mass transfer coefficient. Okay, the mass transfer coefficient, this is the first term, that is a film resistance, macropore resistance, micropore resistance. Everything we clubbed into one mass transfer coefficient and used it here, okay, to define dou q by I by dou t, and we are calling this as a linear driving force model. Okay, there are few advanced models like QDF is also available. Okay, you can that is quadratic version of this, yeah, driving force model. So with this we are completed the mass balance equation. Okay, first we looked into the packet bed, then we looked into the particle, how the mass is transferring or mass is accumulating inside the particle, inside the pellet, then followed by the particle. Okay, that completes the mass balance, how the mass that is accumulating in the system. Now coming to the important factor, that is adsorption equilibrium. We have multiple adsorption isotherm models, okay, in the literature. A few I can show now. Langmuir model, very famous model. Then we have Freundlich model. We have Toth model. Toth and dual site Langmuir and Langmuir-Freundlich, these are advanced models and actually developed on the basis of Langmuir and the Freundlich models. Okay, by overcoming all the limitations that we had for Langmuir models. Okay, by overcoming the assumptions that we made while developing these models. Okay, these are very interesting models. So we will look in the coming tutorial. Okay, we will try to find these parameters. So except pressure and the temperature, okay, and also the adsorption term, so adsorption uptake term, okay, remaining all are unknowns. Okay, so now the question is how do we estimate those unknowns, okay, so that we can use this Q star in our mass balance equation. Okay, that is the estimation of these parameters we will learn in the coming tutorial. Okay, so this looks complex, but if you carefully observe, this is actually developed from the combination of Langmuir and Freundlich, where there is an exponential term that is here, the k naught multiplied by exponential of minus delta h by RT, that represents the heterogeneity of the surface. Okay. So now moving to this energy balance equation, how many energy balance equations we need? Question is straightforward. We have how many phases? 2 phases. We need 2 equations. Gas phase energy balance equation we need, and also the solid phase energy balance equation. Solid is our adsorbent. Okay, this is an exothermic process, and the temperature increases and temperature changes during the adsorption. So we need to incorporate those adsorption, those temperature variations. Okay, so I will show the equation. Okay, this is a conduction term. Okay, that is followed by how the temperature changes. This is a convection term, and okay, this is a temperature accumulation, and there is the adsorbent tank. Okay, we need to consider how the temperature changing from the bulk gas phase to the tank. Okay, and also the bulk gas phase to the adsorbent. Okay, these are heat convection terms that we are considering for the heat transfer between these solid to the gas phase, and also the gas phase to the wall of the tank. Now coming to the solid phase energy balance equation, okay, we have this is for adsorbent. Okay, the adsorbent, how the heat temperature of the adsorbent that is changing with respect to axial direction. Okay, and how the temperature changing from the gas to the surface of the adsorbent. And what is this term? That is very important term. If we remove that term, okay, we don't get accurate result. The last term. So this is heat of adsorption. Okay, how much amount of the heat that is releasing during the adsorption. Dou Qi by dou T, again going back to our kinetic model. Okay, whatever the information that we obtained from the species balance, that would connect, okay, couple this energy balance with the mass balance equation. There is one more left to estimate the pressure, that is the momentum balance equation. Okay, in bulk fluid flows through the voids of this system. Okay, we have viscous energy losses, okay, also inertia losses. So both we can consider in this equation. What is this equation called? Ergun equation. Okay, this is very famous equation to estimate the pressure drop. Okay, where we have inertial term and also the viscous term. So pressure drop is important, okay, because if the system performance mostly affected if the pressure drop is very high. Okay, the performance it would reduce the working capacity also, and it would affect the productivity, recovery, and power consumption would be high if the pressure drops are very high. So in coming class, coming tutorial tomorrow, okay, we will solve this problem. This is a packed bed that we will consider. This is a zeolite 13x packed bed we will solve, where CO2 and 2 coming the source gas we will take at 298 Kelvin and 1 bar, okay, which is 1 meter length, and at initially it is at 25 degrees Celsius and 1 bar. So these are the initial inlet conditions, how much amount of the CO2 and 2. This is ideal condition, okay. We generally don't get binary components. We will have multiple other components also in flue gases. And we will consider adsorbent in the tomorrow's exercise. And the assumptions, we generally make assumptions to simplify those complex models, whatever the equations, PDEs I have shown, right. We will try to simplify them by making these assumptions. For example, axially dispersed plug flow model that will remove the dispersion term, the second order partial differential equation. Ideal gas is applicable if the temperatures and pressures are at the normal conditions. If we are going for extreme conditions, okay, we need to go for non-ideal gas. And also the linear driving force model, okay, if we are not considering this assumption, then we need to incorporate all those micropore diffusional resistances, everything we need to consider. And also either you can go for Darcy's law or Ergun's law or Navier-Stokes, okay, to get the pressure difference in the bed. Then thermal equilibria. What is this assumption called thermal equilibria? What it will do? So thermal equilibria assumption is useful if the gas phase temperature and the solid phase temperature are same in the bed. I have shown two equations for the energy balance. Okay, it will become one if we are considering this thermal equilibria assumption. Okay, and also there aren't any radial gradients you might have seen in the whole equations. There is no dou by dou r. Every time it is dou by dou z. Okay, that means only axial direction we are solving. We are not solving the radial direction. If you want, we can solve in the radial direction. Okay, the del term in the first mass balance equation we have seen, right, that represents in all the directions. Okay, it incorporates in the radial also. Okay, very important information, all those equations are common for adsorption and also for the reaction. For different systems these are common. What makes the CO2 capture adsorption system different from other systems is these two terms, mass source and the heat source. Mass source is the adsorption amount that is obtained from the how much amount gas that is adsorbed. Again it is going back to the adsorption isotherm model or adsorption isotherm. Heat source is the heat of adsorption. These are the source terms that we get from because of adsorption process. Okay. So there are very important performance metrics. These terms you will hear when you are doing this pressure swing adsorption or vacuum swing adsorption, temperature swing adsorption, are purity, recovery, and the productivity. Okay. So this purity is the fraction or percentage of desired component. Our desired component is CO2 in this case. Okay, in the product stream relative to the total components in that stream. Okay, how much amount of the CO2 coming out. Okay, that is either mass or moles of desired component in the product to the total mass or moles of the product. Okay. Then comes to the recovery, how much amount of the CO2 that we recovered. So recovery is the fraction or percentage of the desired component successfully separated or collected from the feed. Okay, that is mass or moles of desired component in the product to the how many moles or how much mass of this desired component in the feed. Okay. Then there is another term called productivity. Okay, this productivity that quantifies the desired product that is obtained per unit or unit mass per volume of the adsorbent. Okay, that is our productivity. This can be calculated by gas flow rate of the desired product to the adsorbent mass, how much amount of the adsorbent that you are using. Okay. So these are very important terms that we use in CO2 capture by using the adsorption technique. Okay. So we have 5 minutes. Do you have any questions so far? Then we will move to the tutorial session. Before moving into that, if you have any questions, we can discuss about them. So if you recollect what Dr. Debanshu was showing, all those partial differential equations, right? Those are related to the mass, momentum and energy balance that we estimated, we have discussed now. Okay, and also from those partial differential equations are built on the fundamentals which Dr. Ravi was teaching, the breakthrough curves, adsorption isotherm models and all those. This is a combination of both. Okay. So are there any questions from online participants? Okay, great. Tomorrow we will solve this same the example, okay, and example in the Aspen adsorption. Okay, today in this tutorial I will show how to estimate the parameters for the dual site Langmuir adsorption isotherm model. we will start from yesterday's script file, right, where we stopped that yesterday's tutorial 1.